Hello everyone, welcome to my channel. It's me, Dr. V. Jayakumar. I'm making lecture videos for the benefit of mechanical engineering students. In this video, we will solve a numerical problem on balancing of several masses revolving in different planes, which is nothing but dynamic balancing of rotors problem. Before we proceed, please press the subscribe button and hit the notification bell icon so that to get notified whenever I post a brand new video on this channel. So let's get started. We will have a quick recap on the various prerequisite concepts that are required before we solve this problem. As you know, balancing of masses problem can be broadly classified under balancing of rotating masses and balancing of reciprocating masses. We have already completed these two sections. In this video, we are going to solve a problem on third type, which is nothing but balancing of several masses rotating in different planes. The two conditions to be satisfied for dynamic balancing are the resultant centrifugal force must be equal to 0. In other words, the force polygon must be closed. The second condition is the resultant couple about the reference plane must be 0, or in other words, the couple polygon should be closed. These are the two conditions using which we are going to find the balancing masses for the given problem. These are the 4 steps that we are going to follow while solving the problem. Now, let us get on with the numerical problem. So this is the given problem. So problem description might look bigger, but let us not get carried away by that. To better understand this problem, let me take a typical 4-rotor system. Now, we will try to understand the data. I'll go through the problem. A rotating shaft, this is the shaft, carries 4 unbalanced masses, 18 kg, 14 kg, 16 kg and 12 kg. Probably I can call them mass 1, 2, 3 and 4. Masses are given M1, M2, M3 and M4 are given at radii 5 cm, 6 cm, 7 cm and 6 cm respectively. It is not that radii of rotation is same as shown in the figure. So here radii of rotation of those masses are different. So they are given R1 as 5 cm, R2 6 cm, R3 and R4 are given. Next, the second, third and fourth masses revolved in planes 8 cm, 16 cm, 28 cm respectively, measured from the plane of the first mass. So the second mass is 8 cm measured from first mass. This is 8 cm. Then third mass is 16 cm. This is 16 cm. Then fourth mass 28 cm. So they are given the distance between the planes, right? And mass 2, 3, 4 are angularly located at 60 degree, 135 degree, 270 degree respectively, measured clockwise from the first mass, looking from the first mass end of the shaft. So from looking from the first mass end, they have given the angular position. We have to draw angular position of the planes diagram by using this data. The shaft is dynamically balanced by 2 masses, both located at 5 cm radii and revolving in planes midway between those of first and second masses and midway between those of third and fourth masses. What they mean? Right now, this four rotor system is not in balance. In order to make this four rotor system in balance, we have to introduce two balancing masses. First balancing mass is located in between the plane 1 and 2. This is where first mass is located. Where is the second balancing mass? In between 3 and 4. They also have given radii of those planes Rx and Ry. Determine graphically or otherwise the magnitudes of the masses and their respective angular position. We need to determine mx and my, theta x and theta y. So these are the required data. Is that problem clear? As always, we'll write down all the given data. Now, what are the things to be found? Our job is to find mx, my as well as theta x and theta y. So, how many unknowns? Four unknowns, right? Yes. Solution. What are the steps we are going to follow? Of course, those 5 steps. What we will do? I am going to complete first 2 steps now. By using the given data, we are going to draw space diagram or linear position of planes as well as angular position of planes. How many masses are given? 4 masses. Whether do we know the distance between them? Yes, we know. Have they given the location of the two planes at which masses to be found, balancing masses to be found? Yes, they are given. Where is that? One is midway between 1 and 2. Another one is in between 3 and 4. Yes, what is the name of them? Plane X, plane Y. This need not to be drawn to the scale. Okay, just a conceptual diagram. Whether from this view can we get the angular position between the planes? No. So only by seeing the end view, they have given the angles between the planes are given, which is given in the problem. Now mass 1, 1, because theta equal to 0. What is the theta 2? 60-degree measured from M1 in clockwise. What is the mass 3? 135-degree measured from M1 in clockwise. It's given data. What is mass 4? 270-degree. This is known as angular position of planes. Angles to be drawn to the scale. Both diagrams give us position of planes. Okay. Now, step number 2. We need to locate the reference plane. Here we have two unknown values mx and my. They are locating at this plane x and y respectively. Either I can choose x plane as a reference plane or y as a reference plane. Both will do. Okay. So what is a clue? Where we have more number of unknowns, there you have to choose the reference plane. This is my reference plane. I call it as RP. Anything that I measure towards the right of the reference plane, I call it as positive. Any measurement I am taking towards the left of the reference plane, I take it as negative. Now we have come to the third important step. What is that? Tabulating centrifugal forces and couples value. Before going to that, what is the formula to find centrifugal force due to say mass m1? Fc1 equal to m1 R1. What is the couple formula? Force into distance between those two planes is known as couple. M1 R1 L1. For force MR, for couple MRL. So this notation is M in kilogram, radius R in meters. This is M into R divided by omega square. So the unit is kg meter. This is L, unit is meter. This is M or L divided by omega square. Unit is kg meter square. Then angle in degrees. Now we can fill in the table. So plane 1, X is my reference plane, 2, 3, then Y and 4. So for mass 18, radius is given. Do you know mx? No, we do not know mx. Do you know rx? Yes, they are given. These are our unknowns. Just mere multiplication. So we got centrifugal force, Fc. Now we need to find a couple. So what is this? This we have to measure distance from reference plane. For a mass 1, so what is the distance between plane 1 and reference plane? 40 mm. I can write here 40 mm. Mass 1 is located on the left of reference plane. So that means distance is measured on the left of reference plane. So what is the sign? Minus. So multiplying that, I will get. What is the distance between x plane and reference plane? Because x itself a reference plane. So it is 0. So this is 0. Therefore, couple will be 0. Distance is plus 40 mm. So I will be same way I can complete other value. So totally how many unknowns? 4 unknowns. Mx, My, theta x, theta y. We have completed the table now. Step number 3 is done. What is step number 4? We have to draw the coupled polygon. You will have a doubt. Why coupled polygon first? Why not the force polygon? We have to choose coupled polygon first because we have only one unknown in that column. Okay. It is always suggested to draw position of planes, angular position of planes, couple polygon and force polygon on the same side of your paper. So we are going to draw couple polygon. So it is a vector. So to draw the couple, we need magnitude and direction. So magnitudes are available here. What is the direction? As per Dolby's method, we are going to assume the direction of the couple is same as the direction of centrifugal force. For detailed concept, you have to refer to my previous video where I have explained the technical concept involved in it. Just by going through the minimum value to maximum value, we need to appropriately choose the scale before we draw the couple polygon. I have chosen 0.025 kg meter square as the scale. Right. How to start the diagram? Start orbitally anywhere. Let me call that point as some O dash. Now I am trying to draw couple for mass 1. The value is minus 0.036. So I am dividing it by the scale. I am getting 1.44 centimeter line I have to draw. In which direction? Actually speaking, you should be acting radially outwards along this direction. Since that minus is given, I should be drawing exactly in the opposite direction. So from here 1.44, this is my 1 dash. Now I have to go to x0, that means the same point, done. Now third point, 0.0336 divided by the scale, 0.025, 1.344. What is the direction for 2 parallel to this? You should be drawing parallel line from this mass to use the roller scale. Just keep the scale there, simply roll over it, you will get a parallel line. Or the Paka method is what? Using the set square combination for drawing the parallel lines. Okay, what is this dimension? 1.344. So 2 is 10. What is 3? I have to go for magnitude 0.1344 divided by 0.025, 5.376 centimeter I need to draw. The next one is 0.009 my. We have unknown my. Can I draw that vector now? No, because we do not have the magnitude. We have unknown. So do not worry. You move on with next vector, because the order of vector addition will not change your value while doing the vector addition. Vector polygon, right? Force polygon or couple polygon. So that is the idea here. So I do not know about this vector. Time being, I jump to the next couple value. How much? 0.1728 divided by my scale. So I have to draw 6.9. So where is the 4? Exactly perpendicular line. So we have used up all data except one. For a system to be in dynamic balancing, what are the two conditions to be satisfied? Couple polygon must be closed, force polygon must be closed. Whether the couple polygon is closed right now? No. What it means? Now the system is out of balance. How much out of balance? Joining the closing side, you will get, this is the amount of couple that needs to be added, then only the couple polygon will be closed. This closing side must be equal to 0.009 my. Clear? Before going to that, what would be the direction? Couple polygon must be closed. That means it should be towards the origin. This direction is so important. So now what I am going to do, I am going to measure the closing side. I am getting about 4.8 centimeter. Therefore, I can write 0.120 is equal to 0.009 my, or So now we have got the value of my. The next one is, what is the direction of my? In order to obtain the direction of my, draw a parallel line parallel to the closing side. Where? To the angular position diagram. Please check here. From here you draw here. Whether it is moving upward or downward, you see the direction here. It is downwards. And just checking the angle with reference to 1 measured clockwise direction, how much it is getting. I am getting about 25 degrees. There you are. We have completed the couple polygon. Using the couple polygon, we got the two unknowns, namely my and theta y. What is the final step? We need to draw force polygon using which this data. Okay, this is now 0.665. I have substituted my value now. So in the force polygon column, we know all the data except mx. So same way, we are going to draw the force polygon. Closing side give you the remaining unknown value. So going by the minimum value to maximum value, I am choosing my scale as 0.5 kg meter. First one is 1.8. So what is the direction? Towards horizontal here. X, it is unknown. Just skip this step now. Go to 0.84 for mass 2. So 1.68 centimeter. So draw a parallel line. And this next is 1.12. After 3, we have y 0.665. What is the direction? Acting here. So I have to go out here. This is to my scale. So this is my direction. This is for y. What is next? I should be going for 4. How much? 4 is 1.44 perpendicular. Now I should be measuring the closing side. Whether this force polygon is closed? No. When force polygon is not closed, what is the meaning? Force is not balanced. So how much not balanced? The closing side is the magnitude to which we have to add the balancing mass. What is the direction? Always it should be closing. Where we start, there we should end. So that is the direction. This closing side must be equal to 0.05 mx is the value. So measuring this and equating to 0.05 mx, you will get the required answer. So when I have measured for my scale, I got about 0.4. I can write now. I got the closing side vector as 3.4 multiplied by my scale. Now what is the final step? I have to find theta x. How can I find? In order to get the direction of mx, we need to draw parallel line from mx to this angular position diagram, because we have direction here. Okay, how can I measure the angle? So about 35 degree there plus 180, 215 degree is the answer. Now we have obtained all the four unknown values, namely mx, my, theta x, theta y. After adding these two masses, if we run the system will rotate smoothly without any vibration. We mean to say that the system is in dynamic balance. That's it. I have given you a problem for practice for you to try at home and solve the problem using the same procedure and check the given answer. Hope you found this video very useful. If so, like this video, share it to your friends and subscribe the channel and hit the notification bell icon. That's it. Thanks for watching. Take care. Bye.